Okay, it looks like everything's working just fine. So let's imagine a different type of experiment where instead of asking someone characteristics about a talker, imagine playing them a pair of talkers and asking them asking them to judge how far apart the talkers are perceptually on a scale of 1 to 100 with no instructions on what to attend to. Let's see if these work.
Loose, soap, sore, hoop, note, tooth.
So those are just two talkers saying three different words. And imagine that I just asked you to rate how different those talkers sound from one another on a 1 to 100 scale. And we'd give you some practice items so that you could calibrate what you were doing. Let's try another pair.
Gas, said, same, loose, soap, sore.
Okay, so I'm saying this hypothetically here, but I've done it before. So these are tasks where you ask people to make explicit dissimilarity judgments or similarity judgments, depending on whether you ask people to rate how different or how similar talkers are. And what you end up with is a distance matrix. Now, you guys have been working on distance matrices, on your final homework assignment. You're not getting them by explicitly saying how different S and Esh are in those different conditions, but the calculations that you guys have, those confusions that you guys are calculating using the formula that we don't think is perfect, but is serviceable, to use the term from our notes, those are essentially taking your confusions and turning them into a distance matrix. And you can think of these distance matrices as analogous to what you might get for driving distances. And so here are three driving distances from the South Island of New Zealand. From Christchurch to Oamaru, which is a city on the east coast of New Zealand. From Christchurch to Dunedin, another city on the coast. And then from Oamaru to Dunedin, you've got these three different distances. Now, from these three distances, we can construct a map of these three cities where the axes on the map will be north, south, and east, west. And in the little snippet of Keith Johnson's chapter that's posted in the folder for your third homework assignment, you've got an example of this from Dutch cities. And you see, it's really geometry that you're using when you're dividing those distances up. And so we know that the physical distances in the real world are, that the dimensions that separate Christchurch from Dunedin from Oamaru are the north, south, and the east, west dimensions, right? That's already known because we know something about the physical world. But we can use a technique, a statistical technique called multidimensional scaling to fit your speaker similarities into a kind of a perceptual map. And so those scare quotes are there because it's a map, but it's not a map of physical distances the way that we're used to looking at when we see a road map or something. Now, on the road map, you know that the distances are north, south, and east, west, but when you get a map of speaker similarities, you don't know what your own dimensions are. So if we took a set of talkers and had a group of listeners scale their similarities, we would get maps of how the speakers are arrayed, how they're positioned on that map, but we wouldn't know what the different dimensions of that map were. We would have to do a little bit of exploratory work to figure out what the perceptual distances were that drove people's judgments of similarity of talkers. So let's take a look at a two-dimensional map that's based on one particular person's ratings of the similarity of pairs of talkers. I need to put my glasses back on here. And so these are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. These are 12 talkers, and those letters and numbers, those are just arbitrary codes that I gave to identify talkers in my experiment, right? So I had 12 talkers, and I had people rating how similar every pair of talkers were. So we had a distance of BB1 to DD7. We had a distance of BB1 to FF1. We had all pairwise differences were measured in this experiment. And we used multidimensional scaling, a technique that we'll just think of it as a black box, as a magic tool, to get this map, okay? And what we have here is a two-dimensional map. But we don't know what dimensions 1 and dimensions 2 correspond to. We don't know what are the cues that listeners might have been, that this particular listener might have been using when she or he was judging the similarity of pairs of talkers. Well, we know something about these talkers because I did lots of acoustic analyses of their voices. So I know things like the average F1 frequency for all of the vowels I had them say, and the average F2 frequency, and the average fundamental frequency. And I know things about the way they said the sounds S, and the voice onset time of their voiceless stops. So I can look at correlations between where these speakers are on this map and these acoustic variables that I know, and I can make a guess, a best guess, a pretty good guess, about what the particular listener here was attending to, was paying attention to when they were making these judgments. Now, as it happens, dimension 1 here correlates pretty highly for this particular listener with the speaker's average first formant frequency. The y-axis correlates with the average F2 frequency. And so this particular listener was attending to these speakers' overall formant frequencies when they were judging differences. And that might have been because the person was listening for things like how long are their vocal tracts. Contrast that with another listener in the very same experiment, so the same instructions, the same stimuli, but remember, we had no explicit instructions on what people should pay attention to. Well, this listener was a little bit different because this listener paid attention to the first formant frequency and to the fundamental frequency, which we perceive as the pitch of the voice. So this listener was different from the other listener in that this listener's similarity judgments and their resulting similarity maps or similarity spaces were affected by fundamental frequency in the way that the other listeners were not. Now, maybe we can even predict something about these listeners based on their similarity spaces. Maybe that second listener would be more likely to perceive other things that are reflected by F0. So for example, we know that F0 conveys differences in intonation. Maybe that second listener is more adept, adroit, skilled at perceiving intonation than the first listener. That first listener listened more to F2 frequency, or at least we think that listener did because of the way the similarity spaces fell out. So maybe that first listener is better at listening to subtle differences in vowels front-back dimension, because that's what F2 conveys. Okay, so the similarity spaces are just a more exploratory, less constrained way of looking at the perception of talkers. And so just to tie it up here, the reason that this is advantageous is because when we've got similarity spaces, we're not worrying about saying to someone, tell me how much this person sounds like an orthodontist, or tell me how gay this person sounds, or tell me whether or not this person sounds like they're from New Orleans or Minnesota, right? We're just saying, tell me how different these two talkers are. And then by correlating those similarity spaces with different things we know about the talkers, either acoustic measures, as we just talked about, or attributes. So we might have, for example, we might have gay speakers and straight speakers in that set of talkers, and we might find that one listener's similarity spaces really differentiates well between the gay and straight speakers, and another's does not. Well, if the one listener whose similarity spaces differentiates really well between the gay and straight speakers, we might think that that person is more naturally listening for sexual orientation in speech than the listener whose similarity spaces doesn't differentiate between gay and straight. Okay, so let's think a little bit more about talker perception to tie up this unit. There are 4 aspects of experiments that measure talker perception that are relevant. The characteristics of the talkers who are being perceived, the content of the utterance used as a stimulus, and the acoustic characteristics of that signal, what the listeners themselves know, and the kinds of things that we ask listeners to do for responses. We can talk about talker perception in terms of accuracy. And when we talk about accuracy, this is a little look ahead to those of you who are going to take hearing science next semester. We can talk about if we asked you to judge whether or not a voice you heard was a talker that you already knew or already had heard, your answer is going to be yes or no, and the true value is going to be yes or no. So if I played you a bunch of talkers and then we waited an hour and I played you the talkers again and asked you, is this somebody you heard before or not, there are 4 possibilities. One is that you actually heard the talker before and you said no, you hadn't. That's a miss. Okay? So you're incorrect but you're incorrect, and you should have been correct. So you did actually hear it, but you thought you didn't. That's a miss. When you're correct in saying no, so you didn't actually hear the talker and you said no, that's called a correct rejection. When you did hear the talker before and you said yes, you actually heard that talker, that's called a hit. When you said you heard the talker but you actually didn't, that's called a false alarm. And one of the things that's critical in any kind of detection task, this is signal detection theory right here, is that if all you measure are hits, everybody can get 100 if they just say yes all the time, right? So we always want to calibrate our hits against what are called our false alarms, right? So there can't be, you can't get 100 on just saying yes all the time in a detection task. Well, you can if all you measure is percent correct, but if you don't penalize the person for having lots of false alarms, then you get an overly rosy picture of what their actual ability is. Now, what about talkers themselves? Well, some talkers are easier to recognize than others. Think back to our similarity spaces. Some of the talker pairs were closer to one another, i.e. were perceived as more similar sounding than others. And the reasons for this are unclear. Some people simply have very distinct voices. And so you can think right now, if we were in class, I would stop and say, tell me about an actor who has a really distinctive voice. And I'm sure people would come up with lots of different examples. The one that always comes to my mind is Kristen Schaal. So Kristen Schaal is the voice of Louise on Bob's Burgers, the one who wears the rabbit ears. That she was also on BoJack Horseman as an incidental character. She's sort of the resident quirky actress these days. And she's a very distinctive voice, right? Her voice is probably easy to recognize. It's quite high-pitched and it has very high formants. Now, listeners may judge talkers as similar sounding because they are perceived to share a large number of attributes. So if you're the kind of person who naturally perceives things like gender and age and social class from talkers, then you might judge two talkers as sounding similar to one another because they both sound old and male and working class or whatever. Other people might judge talkers to sound similar to one another simply because of raw acoustic similarity. So if two talkers have similar fundamental frequencies and similar average F1 frequencies, you might judge them as similar. And these two explanations are not mutually exclusive. So it could be the case that you perceive two talkers to share a lot of attributes, and it happens that they have a lot of acoustic similarity in their voices. Now, let's talk about how different talkers sound from one another. There is some evidence, and this is evidence that is actually, there's some weak evidence, i.e. plenty of room to do experiments here. There's some evidence that men's voices are more distinct from one another than are women's voices. And this may relate to a new sociolinguistic phenomenon, new to us at least, gender-related differences in the tendency to accommodate linguistically. So when we say linguistic accommodation, we mean in social interactions, people have different tendencies to move together, to move towards one another in the way they behave. So think about talking with somebody else. Everybody has their own vocal tract length, everybody has their own larynx, so you start out the conversation with different fundamental frequencies and different formant frequencies. Over the course of a social interaction where you're each taking turns in conversation, it's been observed that some pairs of people get more similar to one another, and we call this accommodation. So moving towards the sort of mean value for you and someone else. Other people have been observed to move away from each other. So people who have similar voices in an experiment might begin to sound over the course of that experiment more different from one another. Now, a general observation, and this is a very general observation based on not a ton of data, is that women accommodate linguistically more than men. So when women are in conversations with one another, they tend to move towards sounding like the average value for the two of them. So if one woman has a mean fundamental frequency of 150 hertz and another has a mean fundamental frequency of 180 hertz, over the course of that experiment, they'll move toward the mean of 100. Each one of them will move toward the mean of 165. Men have been observed to do this less so. And so it might be that the greater distinctiveness of men's voices is simply because of their decreased tendency to, no, it's the greater distinctiveness of men's voices might be argued to reflect their decreased tendency to move toward similar language styles to their conversational partner. Real-time correction here. Good. Okay, we're going to take a break here only so that each video isn't too terribly long.